Hello. In this short video, I would like to show you how to find Thevenin and Norton equivalent resistances in simple resistive circuits consisting entirely of resistors and independent sources. We're not going to deal with how you'd handle dependent sources in this brief video. So to start out, let's take a look at this problem here I have set up. We're not going to work out the entire problem, but it says, for the following circuit, find the Thevenin equivalent circuit to the left of terminals A and B, and then find the current flowing through RL when RL is 6 ohms. Well, what you could do to find the Thevenin or Norton resistance, because they're identical, keep in mind that the Thevenin resistance is always equal to the Norton resistance. And you can always find it in all circuits by taking the V open circuit between terminals A and B. So what you do is you remove the load resistor out here, and you take this open circuit voltage here between A and B, and you divide it by the short circuit current by shorting this out and then finding that current, calling that I short circuit. It turns out that the open circuit voltage is equal to the Thevenin voltage, and the short circuit current is equal to the Norton current. That's Ohm's law. So you can always find the Thevenin equivalent resistance whether or not you have entirely independent sources or a mixture of independent and dependent sources in the circuit by taking the open circuit voltage between two terminals and dividing it by what the short circuit current would be there. But when you entirely have independent sources like we do in this problem, you don't have to make the problem that complicated. All you have to do is this: remove the load resistor, no matter where it is in the circuit, and place yourself out here. And look in from terminals A and B, and whatever you see looking in there, reducing the sources to 0, it'll always be our Thevenin. It's an easy way of finding our Thevenin and our Norton. So, just like you do in superposition, and you have to reduce sources to 0. So voltage sources you short to make them go to 0, and current sources you open to make them go to 0. It's something you just have to memorize for circuit analysis. Now you can't do it in a lab, but on paper you can do it. You short the voltage sources and you open the current sources. So what I want you to do is look in from the right-hand side and work back toward, in other words, just like you did in simple problems. Look, if you had a circuit that looked like this, where this was some total voltage right here, and you had a resistor there, and you had a resistor here, and then in parallel you had another resistor. Just for the heck of it, let me put that resistor up there. This is R1, this is R2, and this is R3. If you want to find a total current in that circuit, if you want to find IT in that circuit, you had to find a total resistance first. You had to find RT looking in from the source out here, looking in there. To do that, you go to the back of the circuit and you work toward. So you would have moved this R3 down here. It's easier to see that it's in parallel. These two in parallel, R2 in parallel with R3 plus R1. So you would see that the total resistance in that circuit is R2 in parallel with R3, product over the sum, plus the R1. You would see that with no trouble. But look how you analyze that. You're looking from the left, so you go the whole way to the back of the circuit. You go back here, and you work back toward you. Well, you do the same thing when you find the Thevenin equivalent resistance here. What you have to do is you have to go back over to here, reducing all sources to 0, and work back toward you. If you short this out and you open that and you look in, and again, you can only do this when they're independent sources. If you see any dependent sources that look like diamonds, you have to use that formula to find R Thevenin and R Norton. But since we have all independent sources here, do you see that that 4 ohms is in parallel with that 12? I'm starting on the left side and working back. So your R Thevenin in that circuit, which is equal to R Norton, I'll keep telling you that they're the same resistance, is equal to the 4 in parallel with the 12. And then you simply add 1. So 4 in parallel with 12 turns out to be 3 ohms, and you add 1 to it. So that Thevenin resistance turns out to be equal to 4 ohms. That's how easy it is to find the Thevenin equivalent resistance when you have all independent sources. Let's do another one. Let's look at this problem here and see what we end up with. Again, it's a more complicated. They want to find a Norton equivalent to that circuit, but we're not worried about Norton and Thevenin equivalent. I just want you to look at that circuit and see if you can tell me what R Norton is in that. And remember, R Norton is equal to R Thevenin. So all we're going to do to analyze that is it's all independent sources. So you can open this and you can short this, and you're looking in from out here. This is you. And you're looking in from where that load resistor is going to be placed between A and B here when you're all done. And when you look in, you go the whole way to this side of the circuit and work back. And I hope you see 8 plus the 4 plus the 8 all in series, and that's in parallel with the 5. That's in parallel with 5. And when you work that out, you get 20 in parallel with 5. So your R Norton in that circuit is simply equal to 4 ohms. Pretty easy to work those problems out when you have all independent sources. Let's look at another one. Let's say you have a problem that looks like this. Problem number 9. I call it on here. Looks like this. Again, I'm asking for other things here, but it says find the value of RL for maximum power transfer in the following circuit. Well, look, it turns out that for maximum power transfer from this circuit, if you Theveninize that circuit, you get maximum power when RL is exactly equal to R Thevenin. I talk about that in another lecture. In other words, if you vary that and you have your Thevenin equivalent circuit that looks like this. Now, we didn't find the Thevenin equivalent, but let's make this V Thevenin right here. And let's say we calculate the Thevenin resistance up here. We're going to do that in a minute. There's your Thevenin resistance. And then you put your load resistor on out here. So that whole circle part of that circuit, I reduced down to a Thevenin equivalent. And then I put this load resistor out here. It makes things a lot easier for the electrical engineer during circuit analysis. And they want to know, what's the value of RL have to be equal to get maximum power from this circuit that I circled to that load resistor? Well, it turns out it's very easy to do mathematically. I do it in another video. But this is power to the load, and this is resistance of the load. If the resistance of the load is 0, if that resistor and the load was 0 ohms, there'd be no voltage across it. So voltage times current is 0 watts, so you don't get anything. And if it's an open circuit, RL is infinity. You make it on the other end of the scale. You make it infinity, and then the current goes to 0. If it's an open circuit, and you're real high in the load resistance, so I squared R, or V times I, is going to tell you you're back to 0 again. The question is, what does it do in between? Well, it does this. Again, I have this in another video. It reaches a peak and then it's asymptotic like that. It happens that this maximum power to the load, let me call it P to the load max. That maximum power happens right when RL is equal to R Thevenin. So all we have to do to find the value of RL for maximum power to RL from the circuit is look at that circuit and determine what the R Thevenin is. So what we're going to do down here is we're going to say R Thevenin is equal to, and remember how we did that. We removed the load resistor, and since there's all independent sources there, we look in. We remove that, and you're out here, and you're looking in to that circuit, and you reduce all the sources to 0. So you open current sources, and you short voltage sources. And then you start at this end and work back. You have to look at that very closely, but you should see 6 in parallel with 12. That 6 ohm and that 12 ohm are in parallel. And then you add a 3, it's in series, and then you add the 2. And when you calculate R Thevenin, you get R Thevenin equal to 9 ohms. Therefore, RL has to be equal to R Thevenin, which is equal to 9 ohms for maximum power transfer. For maximum power transfer. A little extra words here to help you out. Anytime you see a problem that says maximum power transfer, anytime you see that wording in a circuit analysis problem, it's a Thevenin problem. You have to convert to a Thevenin circuit. You have to convert to a Thevenin circuit. And then, just to continue here briefly, if they ask you what is the value of power that you're going to use, what's the maximum power in watts that can be transferred? We just found what the value of RL is for maximum power transfer from the circuit. What is the actual power? Well, the power in the load max, which would be part B to this problem, and I could prove this, but it's just an equation. It's the Thevenin voltage. We didn't find that, but it's the Thevenin voltage squared divided by 4 times the Thevenin resistance. I mean, the load resistance doesn't even appear in that because Thevenin, R Thevenin and RL are equal to one another. So that is like an equation that you can remember. That's in watts. That's the answer to part B in this problem, although we didn't calculate R Thevenin. I mean, if you work the problem out and you're interested in working the problem out, I worked it out using superposition, and when I did that, this is what I got. I ended up with a V Thevenin equal to 22 volts. And you know what your R Thevenin is. We said it was equal to 9 ohms. And if I plugged it into that formula up there, I got power in the load max. It's just a plug-in. Is 13.44 watts. But my intent on this problem here was just showing you how easy it is to calculate the Thevenin resistance. And one of the reasons why you would get the Thevenin resistance, besides trying to find the complete Thevenin circuit, is to determine what the value of RL would have to be for maximum power transfer. Very, very useful when trying to design an audio amplifier and you're trying to get the most power from that amplifier to the speakers. The resistance of the speakers just have to match the Thevenin resistance of the amplifier. That's all. Hope that helps.